Hi, my name is Linda Ortiz, and this is Lab 2, the motion of a falling object. The goal of Lab 2 is to analyze and interpret the outside forces that are acting upon an object that has been dropped from rest and falls somewhat slowly straight down. From Lab 1, we learned that from Newton's second law, when there is constant velocity, the net force equals zero. Now that there is no longer constant velocity, we're looking at the outside forces, which in this case, in this lab, will be weight force and drag force. For my motion video, I will be analyzing a leaf falling to the floor. Since the leaf is really small, here's an image of it before you see the video. Within Tracker, I specified the video frames, in this case frames 33 through 56. Next, I specified a time step of 0.033 seconds. After that, I used a calibration stick to specify the length of my leaf in meters. And finally, I set up the coordinate system so that the leaf was falling along the negative y-axis. Using point mass, I was able to follow the motion of the falling leaf, and Tracker extracted data that I would later use to plot the observed position versus time. Using Python code in idle, I was able to construct a computational model. This code is quite similar to that of the code from Lab 1, but since we are now dealing with a non-zero net force, I had to update the outside forces of weight and drag. I specified the mass of the leaf, and then specified the initial conditions of position and velocity, as well as the beginning time of 0 seconds. The initial velocity is 0 because the leaf was dropped from rest. Next, I specified the time step. After that, I updated the ending time. With the code already providing Newton's second law, I made sure to update the first outside force of weight, which I specified in my code as W. And then I added W to my net force to analyze the position versus time without drag. I also emphasized a value for the arrow scale, the visual record that a force is acting upon the object. Now I will run the simulation that represents the object falling with the interaction of an outside weight force. The weight force will be represented by a yellow arrow, which I earlier specified with the arrow scale that is pointing down from the ball. The graph is no longer linear as it was in the first lab, as velocity is no longer constant. After looking at just weight force alone, I went back to my Python model to include an outside force of drag along with the weight force. The initial conditions stayed the same for the most part, but this time I make sure to emphasize a constant of b for the drag force. The b value here is 0.0015, a value needed for the simulation ball to arrive at the same predicted position as the observed position of the leaf. Now the net force is inclusive of weight and drag, so in the code I write Fnet equals W plus Fd, and drag is proportional to the square of the speed. And finally, I update a second arrow so that you will visually see a bottom weight force acting upon the ball, as well as an upward drag force. Now I will run a simulation that represents an object falling with the interaction of an outside weight and drag force. The drag force would be the blue arrow that is pointing up, and the weight force is represented by the yellow arrow pointing down. The graph again is nonlinear, as the velocity is changing, in this case slowing down to the drag force opposing gravity. Now it is time to compare the data from Tracker, along with data from my computational models of weight force not including drag and weight force with drag. As you can see, the drag is a significant force for a falling object. Without drag, the object made it to the final position in half the time of an object affected by drag force. In my graph, you can see the difference in velocity changes for a model with and without drag. When there is no drag, the velocity increases as the object falls, but with an added drag, the velocity decreases and the objects fall slower. If we take a look at just the red and blue lines, which represent the Tracker and the model data with drag force, they are quite similar for the most part. But for the moments when they are not exactly the same, this can be explained, because when the leaf fell to the floor, there was air resistance that caused it to fall at an angle rather than in a straight line. On the other hand, in the computational model, there is a constant of b in the drag force that stays the same, so the line is a bit more linear than that of an observed motion. Now to answer the what if question. What model in Lab 2 produces a terminal velocity? Well, to start, terminal velocity occurs when an object is no longer accelerating, in other words, when the net force is 0. In the cases of our Lab 2, in order for the terminal velocity to be 0, the outside forces would have to add up to 0. When there is only an outside weight force, terminal velocity is not met. The net force is non-zero in this case. But when drag force comes into play, then a terminal velocity is reached, for it opposes the weight force, and in a sense cancels it out and makes the net force 0. Now to answer what does it mean. What if an object was initially thrown downward? Would the terminal velocity in this case be the same or different from when the same object was initially dropped from rest? It would still achieve a terminal velocity. It would even reach terminal velocity, or equilibrium if you will, sooner, since the initial velocity would be greater along with the drag force. When the initial velocity is greater than the terminal velocity, the drag force will be greater than the force of gravity and will allow the object to decelerate until equilibrium and a net force of 0 is reached. This concludes my Lab 2 video report. Thanks for watching.